السلام عليكم ورحمة الله وبركاته طالباتي وطلابي الأعزاء. أهلا بكم ومرحبا مرة أخرى. Welcome back in Physical Chemistry Lab 1 lectures. This course will be presented by Chemistry Department, College of Science, United Arab Emirates University. Today's experiment, inshallah, it will be the heat of vaporization. Heat of vaporization. Our objectives for today just determination of the heat of vaporization of different solvents, especially acetone and ethanol. Let's see how we can determine this heat of vaporization. You will see some concepts like heat of vaporization, intermolecular forces, and as one of intermolecular forces is the hydrogen bonding. And we will talk about some thermodynamics and thermodynamics laws, first law of thermodynamic and second law of thermodynamic, and we will discuss the Gibbs free energy, and then we will go through the chemical potential. The vapor pressure, okay, molecules with high kinetic energies usually escape into the space above the liquid and converted from liquid state to gaseous state. With time, as a number of vapor molecules increases above the liquid, some of them strike the liquid surface again, and recaptured by the liquid, which means it returned back again in the process which is called condensation, which is opposite to vaporization process. Okay, with going time at a certain stage, the rate of vaporization equals the rate of condensation. At that conditions, we reach an equilibrium which is called dynamical equilibrium between the vapor and liquid. Now we can define the vapor pressure. Actually, the vapor pressure is the pressure exerted by the vapor in equilibrium with the liquid at a fixed temperature. Once you reach to the equilibrium, you can say about the pressure, it's a vapor pressure. It should be at equilibrium between liquid and gaseous state at certain temperature. Actually, vapor pressure depends on the identity of the liquid, and from the identity we can refer to the intermolecular forces. And our case today we are going to discuss the hydrogen bonding. Also, the vapor pressure depends on the temperature. There is a relationship between the vapor pressure and temperature, which is directly proportional. The vapor pressure is directly proportional to the temperature. Comparing two different solvents like water and ethanol, we will find that the vapor pressure of ethanol is higher than the vapor pressure of water. And actually, this is attributed to the different intermolecular forces between like molecules for each solvent. And especially for water, there are a huge number of hydrogen bonding between water molecules. And as a definition, the hydrogen bonding is electrostatic attraction between the hydrogen atom and any electronegative atoms, and here especially with oxygen. So the number of hydrogen bonding is very, very huge comparing to ethanol. That's why it's quite difficult for the molecules in the liquid state to escape to the vapor state and convert it to vapor. So, but in ethanol, the intermolecular forces is quite weak comparing to the intermolecular forces in water, which is hydrogen bonding. Okay, so it's easy to vaporize the molecule. The molecule, it's quite easy to evaporate or to be in the gaseous state, to vaporize and convert it to gaseous state. That's why the vapor pressure of ethanol is higher than the vapor pressure of water. I'm going to show that in some graphs later on. Okay, in the next slide. Okay, as you see, there is relationship between the vapor pressure and temperature, and this relationship is directly proportionality. So as you see, increasing the temperature of the liquid increases its vapor pressure. If you are going to compare between ethyl alcohol and water as a solvent just at any given temperature, let's see, compare at 40 degree centigrade. See, the vapor pressure of water at 40 degrees is lower than the vapor pressure of ethanol at the same temperature. And that's why the intermolecular forces between the water molecule is higher than the intermolecular forces between the ethanol molecule. So it's easy to evaporize. Okay, to evaporate. Yes. Okay, see, the relationship is directly increasing the temperature increases the vapor pressure. And if you would like to determine or to define the boiling point of any solvent, okay, the definition of the normal boiling point is the temperature at which the vapor pressure of any solvent will be the same like the vapor pressure of that solvent. So at the value of the vapor pressure of atmospheric pressure, which is this value, just draw a line which is parallel to x-axis, and once it intersects with the curves, this is the normal boiling point of ethanol, which is 80, and this is a normal boiling point of water, which is 100. Okay, and see here you can also comment on that figure with respect to the boiling point. The boiling point of water is higher than the boiling point of ethanol. Do you know why? Because the intermolecular forces here, which are hydrogen bondings or hydrogen bonds, which is stronger than the intermolecular forces between the ethanol molecules. Okay, great. Okay, suppose a pure substance A, which is presented in both liquid and gaseous state. Suppose you have a pure substance, for example, A, which is presented in both status, liquid and gaseous state. Okay, A in the liquid state and A in gaseous state respectively, at a certain temperature T and pressure P. Actually, at equilibrium between the vapor and liquid, you could say that the chemical potential of liquid state at constant temperature and pressure will be the same, the chemical potential of the same substance in the gaseous state at the same conditions, constant temperature and pressure, where mu A and L and mu A gaseous state are the chemical potentials of liquid and the vapor pressure, of liquid and vapor A at constant temperature and pressure respectively. Okay, now we have mentioned chemical potential. Chemical potential actually is the partial molar Gibbs free energy. If you know Gibbs free energy, which is given by J, uppercase J, okay, when you divide it with a number of moles, you end up with the chemical potential. So the chemical potential is the partial molar Gibbs free energy, which is given by this relationship, mu I. It's the partial differentiation, partial derivatives of Gibbs free energy with respect to Ni, and other parameters will be constant, pressure and temperature, and any number of moles of any substances other than I. Okay. Before going more further, I'm going to revise a little bit about the first and second law of thermodynamics. The first law of thermodynamics is given by the following: du equal dq minus dw, where du, the change or the derivatives of internal energy, and q, the amount of heat liberated or absorbed by a system, minus dw, the work. It could be done by the system or done on the system. Okay, the work equals to B dV and Q equals T delta S. If you substitute by this two parameters in the first equation, you end up with du equal TdS minus BdV. Okay, just remember this one. The second law of thermodynamics and the Gibbs free energy. The Gibbs free energy is given by H minus Ts, where G, Gibbs free energy, H, enthalpy, and T, temperature, is the entropy. If you take the derivative, or if you take the derivative, so you are going to discuss the change in these parameters, you end up with dg equal dh minus delta t and s. Delta g equal delta h minus delta t s. Okay, just if you are going to do the derivatives, so the change in delta g will be the same delta h minus t as a constant, and the delta s is variable minus s as a constant, and delta t as a variable. So at constant temperature, this term will be 0, so we end up delta h minus t delta s. Okay, great. So the enthalpy is given by this equation. The enthalpy from the first law of thermodynamics equals the internal energy plus BV. If you are going to talk about the change, delta H will be delta U plus delta multiplication of P and V, which can be replaced by these two terms. And at constant pressure, you can remove this one, V delta B, because it's a constant. So you end up with delta U. Just rearrange this equation, you end up with delta U equal TdS minus P delta V, and you end up with the change in the Gibbs free energy will be V delta B minus S delta D. Okay, just remember this equation we are going to use later in once we use smaller Gibbs free energy, as I'm going to show you later on. So second law of thermodynamics for the and the Gibbs free energy is given by this one, delta G, change in delta G equal V delta P minus S delta T. We have already defined the chemical potential by molar Gibbs free energy. Okay, just mu I will the partial derivative of G with respect to the number of mole I, for example. So you end up with d mu when you do the differentiation with respect to Ni. So d mu I will be volume I dP minus SIM dt, where V is the molar volume and S the molar entropy. Okay, again, suppose you have pure liquid. This is we have already discussed before. Pure substance A, which present in both liquid and gaseous state, which they are in equilibrium. So the chemical potential of liquid at constant temperature and pressure will be the chemical potential in the gaseous state at constant temperature and pressure, where mu A of gaseous and mu A of liquid, mu A of gaseous are the chemical potential of liquid and vapor respectively. And we have already known that the chemical potential is the molar Gibbs free energy. Okay, suppose a small change in the microscopic variables T and P, the temperature will be increased by delta T, and pressure will be increased by dP. Okay, applying this condition in the previous equation, so the chemical potential of liquid state of substance A plus the change of the chemical potential due to the changing of the microscopic parameter T and P will be the mu A of the liquid state. Will be the same, okay, of the gaseous state plus the change of the chemical potential due to the change of the microscopic parameters, temperature and the pressure. From the previous equation in the previous slide, this term, okay, will be the same like this term. They can be cancelled, okay, since the chemical potential of liquid and the vapor A at T and B are equal, so you end up with d mu A of liquid state will be the same d mu A of the gaseous state. Okay, that's good. So the differentiation of d mu, okay, will given by this equation. The differentiation, we have already known that this relationship we have already derived before. It will be V dP minus S dt. S dt, where VIM and SIM are the respective molar volume of substance I and respective molar entropy of the substance I. So VIM, the respective molar volume, and SIM, okay, the molar entropy of substance I. Okay, that's good. Just we use this equation and substitute in that one. We substitute in the liquid state and in the gaseous state. Okay, we end up with this equation. Okay, so we are going to replace just only, we put it for the liquid, which equal to the gaseous state. See, VMA with in liquid state dP, entropy of substance A, molar entropy of substance A in liquid state will be the same in gaseous state. Just rearrange this equation and get in one side dP by dt, you end up with the change of the molar entropy divided by the change of the molar volume. So dP divided by dt will be the change in the entropy, molar entropy, divided by the change of the volume, molar volume, where dVm and delta Sm are volume and entropy changes. That's good. Remember this equation. Okay, consider the isothermal phase transition of A liquid to A in the gaseous state. The Gibbs-Helmholtz equation for this transition, delta G equal delta H minus T delta S. Okay, that's good. At equilibrium, delta G actually equals 0. At equilibrium, the change of the Gibbs free energy will be 0. So you can get delta S from this equation. It will be the delta H of vaporization divided by temperature. The enthalpy change of vaporization divided by temperature. Just substitute this equation we have already got before, the dB by delta T, the change of entropy, molar entropy, divided by the change of the molar volume. Just substitute delta Sm with this one, you end up with this equation. dP by dt, it will be delta H divided by T delta Vm. And this equation, it's a very, very important, which is called Clapeyron-Clausius equation. And this one we are going to use today for determination of the heat of vaporization. How we can do that? Let's see. Okay, the change of the molar volume will be the molar volume in the gaseous state minus molar volume of the liquid state. Actually, this part or this term is quite higher than this one. So you can neglect the volume in liquid state. Molar volume Vm in gaseous state greatly exceeds the molar volume in liquid state. So you can remove this one. And the molar volume of the gaseous state, you can get it by approximation or by using ideal gas law. Delta Vm equal this delta Vm, it will be this one, and this one will be given by the ideal gas law RT divided by P, where N equals 1. It's a molar, 1 mole. Just substitute by delta Vm in the previous equation, this one. So by this value, you end up substitute in the Clapeyron-Clausius equation, you end up with this one. Okay, it's quite difficult to deal with this small amount, so you need to integrate to convert it from differential equation to integrated equation. Very simple. Okay, the integration of this one will be lim p, and you have limited integration, so it will be lim p minus lim p dash, and this one come to the right hand side. These are constant, and 1 over t squared, its integration minus 1 over t, just only minus 1 over t, and you have limited integration, so it will be 1 over t minus 1 over t dash. Okay, that's good. So if you plot a relationship between lim p and 1 over t, you will get a straight line. Let's see, just we are going to some rearrangement. This equation, this is constant, and also, okay, just rearrange it. This term is constant, and this term also, all parameter or variables in it or parameter in it are constant. So you can collect them in one constant. It will be this one minus delta H, molar delta H of vaporization divided by RT. So if you plot a relationship between lim p and the 1 over t, you get straight line, okay, with negative slope, and the slope will be delta H divided by R. R is constant, so you can determine the heat of vaporization of any solvent you are going to use using this equation. So this equation predicts that a plot of lim p versus 1 over t should be linear with negative slope, which is given by delta H divided by R. So the curve will be something like that one. So it's very easy. It will be y equals something, okay, and this is the slope. Just take this slope and divide it by R, which is ideal gas constant. You can determine the heat of vaporization. The heat of vaporization. Very, very good. Okay, now we are talking about vapor pressure and how we can determine the vapor pressure of a solvent. There are two methods we can determine the vapor pressure. The static one, which is given by this equation, okay, static method, or determining the boiling point at different way. The static one just to determine the okay, the first one, static one, or determining the boiling points at different pressure. Okay, these are two methods who are going to determine the vapor pressure at different temperature. How we can do that? Okay, we are going to use that setup. This is a liquid under concentration, and we have vacuum here, okay, just to remove all air above the surface, and this is a water pass. Very good. Just at first temperature, let the system sometimes to create an equilibrium between the vapor and the liquid. So once you reach this equilibrium, you can determine the vapor pressure of that solvent. And the vapor pressure will be the difference in the mercury heights in both in U tube, U tube, U tube. Okay, just evacuate the air, let the liquid to evaporate till the equilibrium, measure the vapor pressure. Okay, now you have the vapor pressure at certain temperature of the water bath. Okay, just change the temperature of the water bath again and stay some time till you reach the equilibrium and determine the vapor pressure. So change the water bath temperature, okay, and repeat 1, 2, 3 to determine the vapor pressure. Okay, in this method, we change the temperature and determine the vapor pressure. The second one, just determination of the boiling point at various values of the pressure above the surface of the liquid. Okay, this is the setup in other visualization. It looks like that one. So you hear air inlet, and here vacuum to vacuum pump, okay, just to get air out, so to say, and you have here the solvent under concentration, so to say, good, and just evacuate this one, and you can okay, you can determine the vapor pressure, and then this is boiling point apparatus. So you can change the vapor pressure by pushing air inside and determine the boiling point, or you can evacuate the pressure and determine the boiling point. Okay, great. So in this one, we change the pressure above the surface and determine the boiling point. In the previous one, we change in the static one, we change the temperature and determine the vapor pressure. So our experiment, the objective just determine the rate of vaporization of ethanol and the acetone. You are going to use, or you are going to you are going to use the Buchner flask temperature and pressure sensors to determine the temperature and the pressure, and the solvents under consideration, ethanol and the acetone. The procedure, just add 15 milliliter of ethanol and 250 milliliter Buchner flask, and just add few boiling beads, okay, to prevent the strong boiling. Then place the flask on the hot plate. Okay. Once the liquid boils, allow few minutes boiling in order the vapor of the liquid. I'm sorry. Okay. Once the liquid boils, so the procedure, just add this one amount of milliliter in this Buchner flask, and add some boiling beads which prevent strong boiling of the solvent. Just place the flask on the hot plate, and once the liquid boil, allow few minutes boiling in order the vapors of the liquid to fill the flask. Then insert the rubber stopper with the temperature and the pressure sensors. Remove the flask from the hot plate and place it on the bench top. Just attach the sensor to the computer to collect the data, and start collecting the data using like Pro device. Just to continue the data collection until the temperature drops to 30 degrees centigrade, and repeat this procedure with acetone. I'm going to show you a video how to do the setup and so on. This one, okay? Okay, this is Lager Pro device, okay, the data collection. And this is the Buchner conical flask. Just add some, you should measure 50 milliliter of using measuring stand of the solvents you have. Then add boiling beads, and put in the hot plate, and stay some time till you till the solvent boil for some minutes. We can accelerate it a little bit. Okay, just boiling and let it for 2 minutes boiling, so to say. In order to the space above the surface will be filled with the vapor, will be saturated with the vapor. Okay. Now we are going to fix the sensors. The temperature sensor will be from the above. This is Bochner flask. Okay, and be sure you close it very carefully, and there is no any release of the vapor from this one. And the pressure sensor from the side, from that side, not from the top. And be sure that there is no any release of the pressure from here. Okay, and then start collecting the data. Okay, and you see the temperature with pressure. The temperature, this is the pressure value, and this is temperature. Temperature is decreased, and also the vapor pressure will decrease till you end up. Okay, just go ahead. See, with time the vapor pressure is decreasing, and also the temperature is decreasing. And keep collecting the data. Okay, and this is for ethanol. And so on. This data you will plot temperature against pressure, and you get some curve, something like, okay, I have already showed it before. It's a directly proportional, and this pressure are going to convert this value to ln. Take the ln for the pressure value, and the reverse of the temperature, the reciprocal of the temperature in Kelvin, and just plot it. Keep collecting the data as you see. You will need later on. Okay, in the data analysis, and the report include two graphs. Okay, you should include two graphs, pressure as a function of temperature, and ln P as a function of 1/T. You need to determine the heat of vaporization for both liquids, acetone and ethanol, and discuss the difference in the value of delta H of vaporization. You will find one is higher than the other. You should comment why, and you should refer to your comments in the intermolecular forces between like molecules in each solvent. Just search the web or the literature for the rate of vaporization of the solvents you used, and compare the value you calculate with the literature one. And now you can calculate the percentage error of delta heat of vaporization. The first plot will be something like that, plot of P against temperature. You will see that increasing the temperature, the vapor pressure will increase directly. And if you'd like to determine the normal boiling point just at 1 atmospheric pressure, just plot a line which parallel to the temperature axis, okay, and it will intersect all curves. So the boiling point of that one, it will be that one, and for water it will be the yellow one. Okay, the second plot, just to get the length this value and 1/T this value. Okay, here you can use Celsius temperature directly, but in this one you should convert it to Kelvin 1/T in Kelvin. So ln P against 1/T in Kelvin, you get a straight line with negative slope, from which you can determine the heat of vaporization. The heat of vaporization, just divide the value you get by ideal gas constant. Okay, good. And with this one, thanks God, alhamdulillah, we have already finished the experiment number four, which is the heat of vaporization. And I hope everything is clear for all of you. And if you want any explanation or any question, just ask me. Inshallah, I'm going to reply you immediately. And until we meet again, I wish you all the best. And bye bye. Wassalamu alaikum wa rahmatullahi wa barakatuh.